Hello everyone, welcome to my channel Master Computer Science subject. Today in this video we are going to discuss about the topic input buffering in a lexical analysis. Before that, just I want to recapitulate what is the role of lexical analyzer. Lexical analyzer reads the source program whichever we have written in high level language, and it reads the program character by character and it generates a stream of tokens. Okay, now what is input buffering in lexical analysis? So a program is stored and the program needs to be buffered at a temporary memory space when the lexical analyzer is reading it. So now here objective is to speed up the reading of the source program by the lexical analyzer. That is the objective, right? But what is the challenge we face? The challenge is the lexical analyzer always looks one or more characters while reading the source program beyond. It reads one or more characters beyond before it reads or it understands the right lexeme. Okay. Now why it looks at least one additional character ahead or one additional character beyond? Now we can understand that from an example. For instance, we may use operators like this in our program while writing the program: minus, equal to, or sometimes this less than symbol. But when the lexical analyzer reads this character, just by reading this character, it cannot come to the conclusion it is minus operation, because this symbol may be followed by this operator, then the operator itself is changing. Right. Similarly, if there is an equal to operator, just by reading the equal to operator, lexical analyzer cannot come to the conclusion it is assignment operator. Because this equal to may be followed by another equal to, which gives a meaning it is equal to operator. Similarly, this operator may be followed by another equal to operator which is less than or equal to. So, lexical analyzer, when reading the source program from the input buffer, it always needs to look ahead one or more characters to identify the right lexemes. So whenever it looks one or more characters ahead, it adds additional overhead for the lexical analyzer. So the objective is, it is actually putting a break for reading the source program. It is not letting the lexical analyzer to read the source program in a speeder manner. So in order to speed up the reading of the source program, we go for a two buffer scheme concept. This is the solution which handles the large look aheads safely. Right, now we understand what is this two buffer scheme. Two buffer scheme means there are two buffer pairs. Okay, why do we need these two buffers? Once again, we recollect the reasons. The amount of time taken to process the characters, that is one reason. Another reason, to process large number of characters during compilation. And of course, the known reason is always the lexical analyzer looks one or more characters ahead. Because of all these reasons, we go for a specialized buffering technique is two buffer. Okay, now there is a picture. This picture gives you the imagination where the program is available. From this buffer only, the lexical analyzer reads the source program character by character from left to right. Okay, imagine there are two buffers. You can imagine that the two buffers are present sequentially or in parallel also. And you observe that at the end of the buffer there is EOF, which indicates the end of file or end of the buffer. This is known as sentinel. This is known as sentinel. Now we are going to understand this two buffer scheme from this example. So what is the statement available in the buffer? E equal to MC square. This is multiplication operator. This is exponent operator. When this is read by the lexical analyzer, it generates these set of tokens. E is an identifier and its attribute value is 2. This is the token name and this is the attribute value. What is the purpose of this attribute? This attribute may tell the position of the symbol table where the information about this identifier is available. The next token is an operator, assignment operator. The next token is identifier, which is for M, and its entry value is given as 3 in the symbol table. Star is an operator. Next is an identifier which is created for C. Then this is exponent operator, and we have a number whose value is 2. These are the stream of tokens generated by the lexical analyzer. Okay, how this two buffering scheme is handled by the lexical analyzer. Imagine this is the beginning of the statement. Now the lexical analyzer reads, there are two pointers pointing to the same character. One pointer is lexemeBegin, another pointer is forward pointer. So let me write it in a very short form. LB is lexemeBegin and this pointer is forward pointer. This lexemeBegin pointer moves from one lexeme to another lexeme. So between the lexemes, this forward pointer scans the program. Okay, now let us try to understand from this given example how this two buffering scheme is implemented. So the first character is pointed by this two pointer. Now only this forward pointer moves. Now forward pointer is pointing to the blank space. Whenever there is a blank space or a new line character, it is ignored by the lexical analyzer. We know that. And this blank space is not a part of an identifier or a keyword. So now the lexical analyzer has understood this is a meaningful lexeme. By the way, it generated this token. Right. Now, lexemeBegin will set to this equal to now. And forward is also set to this because forward ignores the blank spaces. lexemeBegin as well as forward, both the pointers are pointing to the equal to now. Now forward pointer alone keeps moving in the right hand side direction. Now forward pointer moves in this direction. Now as soon as it sees the blank space, it knows that blank space is not a part of this lexeme, and at the same time it has to ignore the blank space. Now the lexical analyzer has understood till now whatever it has read is a meaningful word, which is nothing but a lexeme. So it tries to match with the corresponding token. That's why it generated this token that equal to is an operator. Now the forward is pointing to this, actually it is at the right end of this blank space. Next to this forward pointer, lexemeBegin is set now. Now forward pointer continues to move from here. It reads M. Just by reading M, it does not know it is an identifier. So further it moves. It continues to read. It looks ahead one symbol. When it reads the star operator, it knows that the star is not a part of the previous character what it read. So this is some different pattern. The star is a different pattern. So what it does, now the forward pointer retracts. Retracts means goes back to the previous position. As of now, this M is pointed by both the pointers, lexemeBegin as well as the forward pointer. That's how it has identified a new lexeme, which is ID, 3. Now lexemeBegin starts pointing to the star operator. Forward continues to scan from here. Just by reading the star, it cannot decide it is a multiplication operator. So forward pointer looks one symbol ahead. So forward pointer moves here. What it reads the character C. It knows that the C cannot be a part of an operator, or the operator cannot be a part of this meaningful lexeme. So the lexical analyzer finds a match or a pattern up to this star. That's why it returns a token star. Likewise, it continues to read the rest of the complete statement. In case, suppose imagine now the C is pointed by lexemeBegin as well as forward pointer. Forward pointer moves here. By reading the star, it stops because it knows the star is not a part of either an identifier nor a token, because the C can be a token or an identifier according to lexical analyzer. So it stops and it retracts back in this case. Whenever the lexical analyzer reads a white space, in that case only the forward pointer does not retract back. Other than that, forward pointer retracts back to its previous character if it is not finding any pattern match. So it reads the C, and that's why it returns a token ID comma 4. Now lexemeBegin and forward is pointing to the star and continues to read. Forward scans the star, forward moves right and further scans the star. Further forward pointer moves to point to this 2. Once it reads 2, it recognizes that till the last character whatever it reads is a meaningful lexeme. So where is a lexemeBegin pointer now? LexemeBegin pointer is pointing to the first star in fact. So it is pointing to this star. So forward pointer retracts back. From lexemeBegin till forward, whatever the symbols are there is nothing but a next token. Likewise, it completes the reading of the input buffer. Right. Now we understand the two buffer scheme. Two buffers are designed just to speed up the reading process. Two buffers each of size n. This n is usually the size of a disk block because one simple system call, that is read operation, must be enough to fill one buffer. I mean, every time there must not be a call to read a character from the memory. So one single read operation must be sufficient to fill one buffer. That is why usually the size of the buffer is designed with the size n, and n is usually the size of disk block. Every buffer end is indicated by EOF. That is why here it is written with EOF. Okay. Now there are two pointers. One is lexemeBegin, another one is forward. What is the purpose of lexemeBegin? It reads from lexeme to lexeme. What is the purpose of forward pointer? It just scans every character from left to right between the lexemes. Scans ahead until a pattern match is found. Right. Once the lexeme is determined, forward is set to the character at its right end, or sometimes it may retract one position to the left. This I explained when it will happen. If it reads the blank space, forward is set to it the right of the blank space. Suppose there is no blank space between the lexemes, and if it reads one character ahead, and if that character is not part of that particular lexeme, the forward pointer retracts back. lexemeBegin is always set to the character immediately after the lexeme is found. Once the lexeme is found, it will be pointing to the character next to the lexeme. So in simple words I can say lexemeBegin pointer reads from one lexeme to another lexeme. For example, suppose there is a statement int I comma j. We know that int is a lexeme because it is a keyword. I is a lexeme because it is an identifier, comma is a special symbol, J is another lexeme which is an identifier. So lexemeBegin starts reading from I, forward continues to read and it identifies the lexeme and it returns a token. From I, the lexemeBegin jumps to this I, which is the next lexeme. This jumping is happening with the help of the forward pointer. So where the forward pointer ends, next to the forward pointer, lexemeBegin is set. So for every character read by the lexical analyzer, in fact there are two tests conducted by the lexical analyzer. One is to determine what character is being read. Another to determine whether it has reached the end of the buffer. Suppose if it reaches the end of the buffer, it is the time to reload the next buffer. Okay. Now there is a code with respect to this lexical analyzer. There is a switch case. Here value is given the forward pointer which is getting incremented. Forward is a pointer here. This code is written in Java. The case is end of file. If the case is end of file and if the forward is at the end of the first buffer, if the forward pointer is pointing at the end of the first buffer, then it is time to reload the second buffer and it is time to set the forward to the beginning of the second buffer. Else if the forward is at the end of the second buffer, it's time to reload the second buffer. It means it has finished reading the first buffer. So it's forward is at the end of the second buffer. It's time to reload the first buffer. because it has finished reading the second buffer, so it is going to continue to read the first buffer. Then forward pointer must be set to the beginning of the first buffer. Otherwise, if both the cases are not there, it means it is a time to terminate the lexical analysis, because when the program keeps loading the buffers, at one point when the program is ended, it is not necessary that the program has to be ended at the last position of the buffer. Program may end here. Once a program is ended, the next cell will be filled with the EOF. So you can find EOF at 3 locations. At the end of the buffers or somewhere in the middle. If it appears somewhere in the middle, it means the program itself is ended. When the program itself is ended, it is a time to terminate the lexical analysis. I hope you have understood the concept of input buffering in the lexical analysis. In the next video, I will give you the whole picture of the lexical analyzer with whatever the concepts we have discussed till now. I request all of you to share, like, comment and subscribe to my channel. Thank you.